So hello everyone, this is lecture 61 for the mathematical physics. In the last lecture we were discussing about the fundamental theorem for the curve, that is Stokes theorem. We have discussed an example in the cylindrical symmetry, discussed in the Cartesian symmetry. So let's do one more example in the spherical symmetry also. So that is your Stokes theorem, curl of A dot dA will give you your line integral A dot dl corresponding to that surface. Okay. So let's A is given from this r cos square theta r cap minus r cos theta sine theta cap plus 3r phi cap. So this is your vector field. Okay, it is given in the spherical coordinate, and you need to find this. For this, you need to verify this result for this surface. So let's see. So we can draw this plot in the known form. We already know. So we can draw it like this. Now see, this surface is covered by these lines, first, second and third. So we'll find the line integral, then we'll compare it with the del cross A dA, then we'll see that if they are coming equal or not. So for this first line or the first segment, r is changing from 0 to 1 and phi is fixed for this and theta is fixed for this. So theta is pi by 2, phi is 0, r is going 0 to 1. So dl will be dr r cap. So a dot dl, from here you can calculate if dl is this. So it will be r cos square theta dr. Now integral will give you 0. Why? Because theta is pi by 2, you substitute here. This is fixed for this segment, so it will give you 0. For second segment, r equal to fixed, so r equal to 1, that is radius is given, that is equal to 1, so that is given. So that will be fixed, and phi is changing 0 to pi by 2 and theta is fixed is pi by 2. So this will be this. Now dl will be r sin theta d phi cap. So a dot dl, okay, you can calculate this directly. So it will be from here 3r then r sin theta d phi will give you r square sin theta d phi. Now phi is going from 0 to pi by 2, so it will be 3 and theta is pi by 2, so this will be 1. So this will be 3 d phi, and phi d phi will give you phi here, so it will be pi by 2 minus 0, so 3 pi by 2 will be your answer for this second one. Now for this third one, r is going from 1 to 0 and phi is pi by 2 fixed and theta is fixed, that is pi by 2. So for this dl will be dr r cap and a dot dl will give you r cos square theta dr. Again theta is pi by 2, so this will be 0 because of cos theta. So this third will be 0, so complete line integral will be 3 pi by 2. Now let's check if the left hand side or this result give you the same or not. Let's find the curl of A. So for this vector, if you find the curl, we already find this value. So this curl of A is came out to be 3 cot theta r cap minus 6 theta cap. Now what you need to do is you need to find the dA also. So for this surface, what will be dA? So see, for this surface theta is fixed, that is pi by 2, so d theta will be 0 and direction will be theta cap. For this it will go like this. You can find direction by the curling your fingers. So direction will be theta cap and area will be d theta equal to 0, then you will get d phi and dr. So your dA will be minus r sin theta dr d phi theta cap, and theta cap will be in negative direction because theta is going this direction. So this direction will be theta cap and this will be minus theta cap, and you are getting for this surface direction will be this will be minus theta cap. That's why you are getting minus theta cap here. Now you have dA, you have del cross A. You will just do the dot product. Del cross A and dA will give you 6r dr d phi, where r is changing and phi is changing. R is changing from 0 to 1 and phi is changing from 0 to pi by 2. You can see this. Phi is changing from 0 to pi by 2. So you will just integrate, it will give you r square by 2 and phi will give you pi by 2. So r square by 2 will give you 1 upon 2 because it is 1. So 6 into 1 upon 2 multiplied pi by 2 will give you 3 pi by 2. So see, this is giving you same result as you are getting here. So that's how we verified this. Now let's see some miscellaneous examples now. We have discussed the fundamental theorem for the divergence, for the curl, Stokes theorem, cos divergence theorem. So let's see some miscellaneous example on the everything we have studied. So if A is given this, ay x cap plus bx y cap, where A and B are constants, and this surface is given. So what we need to do is, we need to verify Stokes theorem for this thing, okay, for this segment. Now see, this is a circular shape given in xy plane. So we will convert this into the known form, that is you can write it in this form, xy is here. Now see, in the Cartesian coordinates you can't solve this because this has a circular symmetry, so it can be solved in the cylindrical symmetry, because there we have infinite circles forming the cylinder. So you can solve this in the cylindrical symmetry. So note this thing: if vector is given in Cartesian coordinate system and symmetry of the surface is cylindrical, then use cylindrical coordinate system, and if symmetry of the surface is spherical, then use spherical coordinate system. So let's see how we can change and how we can verify the Stokes theorem when this is satisfying the cylindrical symmetry. So see, dl is dx x cap plus dy y cap for the xy plane and the Cartesian coordinate. Now x is, we know, in the cylindrical coordinates it is r cos phi and y is r sin phi. So if this is your r, so it will be r cos phi x and r sin phi will give you y. From here you can calculate dx and dy. So dx will be minus r sin phi d phi, dy will be r cos phi d phi. Now see, you need to verify the Stokes theorem, so you need to find the a dot dl. So this is a complete circle. So a dot dl is this. So a is this. So how you can find? Now in place of y, what you can write? In place of y you will write r sin phi. In place of dy you will write r cos phi d phi. In place of dx you will write minus r sin phi d phi. So you have to substitute all these values, then you do the dot product. So a dot dl will give you, so it is dx and ay. So ay dx. So in place of a, y is this and dx is this. So I substituted this plus b, and this is r bx, and this is your dy. So that's how you will get, and you have converted it into the cylindrical coordinates. Okay, so you have your a dot dl. Now you have to integrate this, and you will see that here phi is changing from 0 to 2 pi, and r is fixed, so r is equal to 1. Okay, not 1, it is given as r. So you can simplify this equation into the form of this. It will be minus a r square sin square phi d phi, and it will be b r square cos square phi d phi. Now as I told you, phi is going from 0 to 2 pi. So when you integrate this, it will go from 0 to 2 pi, sin square phi d phi and cos square phi d phi. So you can solve this in terms of cos 2 phi. So cos 2 phi equal to 1 minus 2 sin square phi divided by 2. From there you can find the value. When you solve this, you will get pi as your answer. So this is a very trick also there. If you get anything here and you are having as sin square phi cos square phi here, so integral value will be just half of this. So it will be 2 pi by 2. If it was pi by 2 here, so it will be pi by 4 for this. So you can use that trick also, but you can find the manually. Your answer will be pi, and for this also answer will be pi. So it will be minus ar square, and it will be br square pi. So you can take pi r square common, so it will be b minus a. So this is your line integral. Let's find the curl and the surface integral, if it is giving the same value or not. So curl of a is b minus a z cap, and you know z equal to 0 for this. So z equal to 0, then this surface dA will give you what? It will give you r dr d phi z cap, because dz is 0. So curl of a dot dA, curl of a is this, dot dA will give you r dr d phi b minus a. Now you will take the surface integral, and here r is going from 0 to r, and phi is going from 0 to 2 pi. Just simply integrate this. It will give you r square by 2, means capital R square by 2, and d phi will give you phi, that will give you 2 pi, so it will be pi r square b minus a. So you are getting the same result as here. So we verified this thing, but main thing what we discussed here, the symmetry. So how you convert this and how you visualize or recognize this that that it satisfy the cylindrical symmetry. Sorry for that, I am having a little cold. So let's move forward. So next example is a equal to a naught z cap. We need to find the, and this surface is given. This is hemispherical surface, and you need to find the surface integral only for this hemispherical surface, not the circular one. So we already discussed this, but let's see how we do here, if in the different symmetry you have. So see, this is given in the, it can be in the cylindrical also, because here is z cap. It can be also Cartesian also. But if you need to find the surface integral for this hemispherical surface, you need to choose the spherical coordinates. Okay, so for this surface, what is fixed? That is r equal to r. So dr will be 0 and dA will be given by r square sin theta d theta d phi r cap. Now you need to find a dot dA. So multiply this, a dot dA will give you a naught r square sin theta d theta d phi. Then it will be r cap dot z cap, and z cap dot r cap is nothing but, we already discussed this thing when we discussed the transformation one coordinate system to another. So that will give you cos theta. So it will be sin theta cos theta d phi. Now you need to integrate this simply. And integration, what will the limit? Here phi is changing from 0 to 2 pi, and theta is changing 0 to pi by 2. See, theta is this angle, so theta is changing from 0 to pi by 2, and phi is changing from 0 to 2 pi. So you substitute these values for means for the d phi it will give you 2 pi, and for the sin theta cos theta you can just divide by 2 and multiply by 2. It will give you sin 2 theta, and sin 2 theta integrate that will give you minus cos 2 theta divided by 2. So 0 to pi by 2, this limit will give you your value. So it will be pi a naught square r square, a naught r square. So that will be your answer. So see, that's how you use this thing here. That is the important thing. You must learn this. Now let's take another example. This is the cylinder given in this system. It is minus h downside and h the upper side of this plane, xy plane. We need to calculate r dot dA for the complete surface. This is a closed surface. Okay, so we need to calculate for all the surfaces. So see how you can find this r dot dA. So you remember what we discussed in the Gauss divergence theorem. So any closed surface covering a surface, so that surface integral will be equal to volume divergence of that volume. Okay, means volume integral. So using the Gauss divergence theorem, we can write this in this form: del dot r d tau. Now see, del dot r will give you 3 because this is your r. So this will give you 3, and this will go outside because this is constant. Now volume of all the system. So volume of this cylinder will be given by this height is h. So pi r square, r is a. So pi a square h will be your volume. So you can directly write this as 3 pi a square h. So see, you don't need to find the surface integral for each and every surface. So if you need to find this, you can just directly write this thing, and it will be 3 pi a square h. So let's verify if this is coming equal to this or not. For the each surface we will find. So this height is h by 2, this height is h by 2. So let's find for the first surface first. This is first surface, this is second, and this curved surface is third. So for this first one, it will be z equal to pi by 2. Sorry, z equal to h by 2. So for that, dA will be dz equal to 0. So dA will be r dr d phi z cap. We are taking in the cylindrical coordinates because we know symmetry. So r dr d phi, and r dot dA will give you rz dr d phi, and it will be, now put the limits. R is going 0 to a, and phi is going 0 to 2 pi. So take this z equal to h by 2 is given, so it will be outside. R dr d phi will give you r square by 2 will give you a square by 2. D phi will give you 2 pi. So it will be pi a square h by 2 for the first surface. For the second surface, this one, for this direction was z cap. For this one it will be minus z cap. So everything will remain same, but it will be dA will be minus z cap. R dot dA will be minus rz dr d phi. And when you solve this, in place of z you will write minus h by 2. So it will come in, it will come again the same value as this, pi a square h by 2. Now let's see for this curved surface. For the curved surface, we know what is fixed. Fixed is radius, r equal to a. So dr will be 0 and dA will be r d phi dz r cap. So r dot dA will be given by xr d phi dz, and it will be c. Now r is given in the Cartesian coordinates, and this is in the cylindrical coordinates. When you do the r dot dA, so r cap will multiply with all the terms, with the x cap, y cap, and z cap. So with the x cap, it will be this r dot x cap. For the y, it will be r cap dot y cap. For the z cap, it will be r dot z cap. Now see, r is in the perpendicular direction with the z. So r dot z cap will give you 0. You can use the table I discussed in the transformation equations. So here, r dot x from there is cos phi, and this is nothing but sin phi. So you will just substitute the values, and now you have r dot dA. You will integrate this. So first we are solving this. It will give you a square cos square phi d phi dz, a square sin square phi d phi dz. You can take the a square d phi dz common. It will be cos square phi plus sin square phi. That will be 1. Now you need to integrate this, and phi is going from 0 to 2 pi, and z is going minus h by 2 to h by 2. So it will be h. H will give you h. Let me show you what will give you. So limits are going from like this, minus h by 2, 0 to 2 pi. So d phi will give you phi, that will give you 2 pi here, and this will give you h. H by 2 minus h by 2 will give you h. So this will be 2 pi a square h. Now you need to add all the surface integrals to get the complete value. So for this one, it was pi a square by h. Pi a square by h will give you 1 pi a square h, because this is 1 by 2, 1 by 2. And this third, it was 2 pi a square h. So total value will be 3 pi a square h. Now see, this value is same as we get here. So that's how we simplify the equations using the Gauss divergence theorem or the Stokes theorem. So you must see what concept we use, how we convert the different symmetry, and how we use the different symmetries, and how we use the transformation things. So you must learn from these examples that thing. That's why I am discussing here. So in the next lecture I will discuss some more examples, some difficult ones. Then you will understand more. So thank you everyone.